Vast cosmos, our universe is a tapestry of cosmic bodies and phenomena, woven together by the threads of space and time. Among these celestial wonders, black holes stand as the most mysterious. These cosmic behemoths, with their gravitational pull so strong that even light cannot escape, have long perplexed even the greatest minds. One such mind who dared to probe these enigmas was the late physicist Stephen Hawking. With his brilliance and tenacity, Hawking ventured into the uncharted territories of these celestial abysses. His groundbreaking work, spanning over 5 decades, has significantly broadened our understanding of these cosmic mysteries. His theories, though initially met with skepticism, have stood the test of time, shaping our perception of black holes and their place in the universe. Who better to guide us through this cosmic journey than the late great physicist Stephen Hawking? Stephen Hawking's journey towards unraveling the mysteries of black holes began in the early 1970s. At this time, Hawking was deeply entrenched in his work on singularities within the framework of general relativity. Singularities, for those who may not know, are points in space-time where gravitational forces become infinite. In simpler terms, they're the heart of a black hole, the point where everything, including light, gets sucked in and disappears. Hawking's fascination with singularities was not a mere academic pursuit. He was fascinated by the paradox they presented. According to the established laws of physics, singularities shouldn't exist, but they do. This led him to question the very nature of black holes. How do they form? What happens inside them? And most importantly, what happens to the information about the matter they consume? In these early years, Hawking proposed that black holes could emit radiation, a radical idea that went against the prevailing belief that nothing could escape a black hole's gravitational pull. He suggested that this radiation, now known as Hawking radiation, could eventually lead to the evaporation and disappearance of black holes over time. This was a bold, daring hypothesis that challenged the traditional view of black holes as eternal, unchanging objects. Hawking's early work laid the foundation for a radical new understanding of black holes. His pioneering thoughts on black holes and singularities set the stage for decades of groundbreaking research, transforming our understanding of the universe and its most enigmatic objects. In 1974, Hawking stunned the scientific community with a groundbreaking idea. Prior to this, black holes were perceived as cosmic vacuum cleaners, sucking in everything that came near them, even light itself. They were seen as points of no return, where matter and energy disappeared forever into a gravitational abyss. However, Hawking proposed something remarkable and counterintuitive. He suggested that black holes were not the insatiable monsters they were thought to be. In fact, they could actually emit something out into the universe. This idea was born out of his deep understanding of both quantum mechanics and general relativity. Quantum mechanics, the science of the very small, tells us that pairs of particles and antiparticles spontaneously pop into and out of existence near the event horizon of a black hole. Normally, they annihilate each other almost immediately. But Hawking proposed that if one of these particles fell into the black hole while the other escaped, it would appear as though the black hole was emitting radiation. This phenomenon became known as Hawking radiation. Now, it's important to understand that this idea was not immediately embraced. The concept that black holes could emit anything was in stark contrast to the prevailing understanding of these cosmic entities. Many scientists were skeptical, questioning the validity of Hawking's calculations and the very premise of his idea. But Hawking was not deterred by the skepticism. He believed in his theory and continued his work, refining his calculations and building a strong case for his revolutionary concept. His determination and resilience were a testament to his unwavering belief in the power of scientific inquiry. Hawking's theory of black hole radiation was a game changer. It bridged the gap between quantum mechanics and general relativity, two fields that had been at odds for decades. It reshaped our understanding of black holes and set the stage for new explorations into the mysteries of our universe. Despite the initial skepticism, Hawking stood by his theory, setting the stage for a new era in our understanding of black holes. Hawking's theory challenged the previously held belief about the absolute darkness of black holes. Imagine a cosmic entity so dense, so powerful that nothing, not even light, can escape its gravitational pull. That was the traditional understanding of black holes. But according to the brilliant physicist Stephen Hawking, that's not the full story. Hawking proposed that black holes aren't entirely black. Instead, they emit what he termed Hawking radiation. A paradoxical concept, isn't it? These supposedly insatiable cosmic monsters, rather than being perfect absorbers, are in fact trickling out tiny amounts of radiation. This theory was a game changer. It bridged the gap between quantum mechanics, the physics of the very small, and general relativity, the physics of the very large. So how does this work? Well, due to the strange laws of quantum mechanics, pairs of particles and antiparticles are constantly popping in and out of existence near the event horizon of a black hole. Normally, they annihilate each other almost immediately, but sometimes one particle falls into the black hole while the other escapes into space. This escaping particle is what we perceive as Hawking radiation. The implications of this concept are profound. If black holes are slowly emitting radiation, then they are also losing energy, and hence mass. This means that black holes are not eternal. They can shrink and eventually evaporate entirely given enough time. Of course, for a typical black hole, this process would take unimaginably long, longer than the current age of the universe. Hawking's theory painted a new picture of black holes not as eternal prisons, but as slowly fading cosmic bodies. This idea has not only reshaped our understanding of black holes, but has also opened new avenues of research in the world of theoretical physics. And even though the man himself is no longer with us, his legacy continues to light the way in our quest to unravel the mysteries of the cosmos. 50 years on, Hawking's theory stands stronger than ever. Just as Stephen Hawking dared to explore the unknown corners of the universe, scientists today have followed in his footsteps, probing the enigmatic nature of black holes with an arsenal of modern tools and technologies. In the last few years, highly sophisticated experiments have given us the first tantalizing hints of Hawking radiation, that elusive phenomenon first predicted by Hawking himself half a century ago. These experiments, while not conducted on actual black holes, have successfully demonstrated the process in a laboratory setting. They've created what we call analog black holes, systems that mimic certain aspects of real black holes, allowing the detection of something akin to Hawking radiation. Though it's not a direct observation, it's a significant step towards validating Hawking's revolutionary theory. The confirmation of Hawking radiation would have far-reaching implications, not just for black holes, but for our understanding of the universe itself. It would be a striking demonstration of quantum mechanics and relativity coming together, a union that has eluded scientists for decades. This would inch us closer to a theory of quantum gravity, the holy grail of modern theoretical physics. Hawking's work has already dramatically reshaped our understanding of black holes. Once thought of as cosmic vacuum cleaners swallowing everything in their path, we now see them as complex and dynamic entities. They are laboratories of extreme physics, testing grounds for our most fundamental theories. This shift in perspective, this reimagining of black holes, is perhaps the most enduring legacy of Hawking's work. His theory has shown us that black holes are not just destructive monsters, but also creators and shapers of galaxies. They are integral to the life cycle of the universe, playing a key role in the formation of stars and even galaxies. In fact, without black holes, our universe might be a very different place, perhaps one where life as we know it could not exist. And it was Hawking who first brought us to this profound realization, forever changing our view of the cosmos. Stephen Hawking may have left us, but his profound insights into the nature of black holes continue to illuminate our understanding of the universe. His legacy, his fearless pursuit of knowledge, is a beacon that continues to guide us,